All right, I went ahead and wrote this example out, so you can pause now if you need to write it down, because these take a little bit of time to do. So we're going to do one example per video. If we're looking at this, I have the area of the region bounded by these graphs. I've got an f of x graph and I've got a g of x graph, right? So we are going to graph these two graphs. And then we're going to say, where is this? Which one's on the top? Which one's on the bottom? And then we'll go with that. So over here, I'm going to just make a grid. Make sure that I have plenty of room here on my graph paper. And then we're going to graph these two. Now I'm going to do two colors just because we can. I've got an f of x there, and we'll go blue, red and blue. That way we can really distinguish between the two of them. All right, so first of all, I'm going to kick out red here. Now this is a quadratic. When I graph a quadratic, I use an X, Y, new Y chart because it is all about patterns and it is very efficient and quick. All right, so it is movement from the vertex is what's going on. So if you know the basics of a quadratic here, then you can do that. If you have not had me in class, most likely you haven't seen this X, Y, new Y chart. If you graph with a T-chart, that's fine. That's totally fine. You can graph this however you want to graph this. But whenever I look at my graph here, I'd come up with an X, Y, new Y chart because I'm taking my parent function and I'm moving from my parent function. So anytime you have just a basic quadratic, I'm just going to write it over here. F of x is equal to x squared, right? Then I'm looking at this basic quadratic. What's my automatic vertex? 0, 0, right? And so then whenever I plug in anything, let's say I plug in a 1, where I have 1 as my vertex. Then I plug in a negative 1. It doesn't matter if I plug in a plus or minus 1, what's my output going to be? A 1, right? So my pattern here for my parent function, whether I plug in a positive or negative 1, I have an output of 1 no matter what. Same thing is happening. What if I plug in a positive or a negative 2? What's my output going to be? If I plug in a 2 there, 4. Every single time, right? That's the basics associated with a quadratic. What if I plug in a 3 just for grins? 9, right. I normally stop it off right here at this 1 and 2 just because, frankly, how many points do you need? So I'm going to get rid of this part here. But that's just my basics of setting it up. I would be happy to talk with you about this more. Feel free to contact me. I'll totally work some problems like this with you. Now, the other thing we know about our transformations here is that my a value is always in the coefficient in front of my squared term. And that's going to tell me, yes, reflecting over the x-axis if I have that issue, if I have any vertical stretching or shrinking going on, right? So that's going to help me there, and that's really what we look at when we have our quadratics. Okay, so what is my a value here? It's a negative 1. We can do all three just because why not, right? But typically I just do the first two. We'll do that for the next one. Then I multiply because my y and my a, that's my vertical transformation. So 1 times negative 1 is negative 1. 4, I multiply these together. 4 times negative 1 is negative 4. 9 times negative 1 is obviously negative 9. Then I cross these middle terms off because I'm going to graph with my x and my new y. This is movement from the vertex. What's your vertex? 0, 5, yes. Because there is nothing next to the x here inside parentheses, so I know it's a 0 from side to side because of our standard form. We know what that looking like, vertex form. And there's a positive 5 back here just because of how it's written. I could rewrite this as f of x is equal to a negative x squared plus 5. Most of the time people look at it that way and you can see what's going on, right? Okay, but so we know that's 0, 5. That's more obvious. And then we graph as movement from the vertex. This is how I graph these. If you graph them a different way and you don't want to try to learn this, that's fine. I'm not trying to do this. Once you get this pattern down, man, you can graph fast. It's super fast and efficient. Okay, so you always start with the vertex. My vertex here is at 0, 5. I'm going to go back to black to mark off my tick marks here. It's up to 5, right? That's actually 6. 1, 2, 3, 4, 5, 6. 2, 3, 4, 5, 6. Okay, we actually want to come up here to 5 because that's where we're looking at this. And so I have a vertex at 0, 5. And then from my vertex, I am going to go positive and negative 1 on the x, positive and negative 1, that's movement, and negative 1 on the y means I go down 1, over 1, down 1. So my next point is here. So you never have to plug in a bunch of points this way. You're using the concept of the parent function in order to pull this off, right? Then on movement is from the vertex. It's always from the vertex. Over 2, down 4. And that's my next point. So over 2, down 4 is going to give me my next point right there. And then I'm going to go back 2, down 4 to get those because we know a parabola is symmetric. Then, just because I already have them on there, I'm going to go over 3. So here we are, 1, 2, 3, down 9. 1, 2, 3, 4, 6, 7, 8, 9. I know I'm going down 9 because it's negative. Oops, I lost my place already. 1, 2, 3, 4, 5, 6, 7, 8, 9. Now I know that's symmetric. A lot of times I like to recount just to make sure that I didn't miscount the first time. And then there's my parabola. And a parabola is a smooth, continuous curve. So it is curvy there, right? Okay, now let's go blue. Now here we're just going to do plus or minus 1 or 2. And I know I've got my x, y, new y chart. Don't forget your A in there. Plus or minus 1, plus or minus 2, 1, and 4. Those are just part of making my chart because those are just straight up part of the basic parent function stuff. Okay, now I see that my A value is a 1. So when I multiply these together to get my new y, I'm not changing anything, but we still write that in there. So my vertex here is going to be 0, negative 3. So I'm going down 3. And then I'm going to go over 1, up 1, back 1, up 1. And then I'm going to go over 2, up 4. 1, 2, 3, 4. Ooh, check me out. And I'm not going to do the next one just because typically I don't. I just wanted to show you guys how I graphed because that's not a common way that most people graph. It's real efficient and quick though, right? I mean, we just graphed those quadratics, boom, just like nothing. Sweet. It is a sweet, sweet deal. Okay, I'm going to zoom this in a little bit here so I can color. Really is honestly what I'm doing. So if I want to find the region between the curves, because that's what it asked me to do, here is my region between the curves, right? This is what we're finding is this region right here. If I just integrate one of these, then that region is just with one of my functions. I want to go between the two. So I'm going to go black on this. This is the top and blue here is the bottom. Do you see that? Okay. Now, here's the key. I'm going to squeeze this in a little bit. When I go to find this integral, I'm going to take my top function minus my bottom function. So my top here is red, my bottom here is blue. But what am I integrating from? What to what? Yes, it's where they intersect. From this value to this value. Because it's the region and I'm looking at this. Here's a negative 2 and here's a positive 2. So my interval is from -2 to 2 that I'm going to integrate from, right? And notice this is dx. So x is the variable that I am plugging in here. Okay, now I'm going to have to go to the next page because I ran out of room here, but do you see what's happening? I've got this top minus bottom, and I'm going from -2 to 2. So when we integrate this, I'm going to go from, let me make this bigger. Here is example 1 continued. I am integrating from -2 to 2. My f of x function is 5 minus x squared minus my g of x function, which is x squared minus 3 dx. Right? Okay, so this is my f of x, and this here is my g of x, and that's what I am subtracting. Now notice I am subtracting this function. So when you subtract, you have to add the opposite, right? So don't forget to do that because you are going to distribute that negative. Then clean it up. Algebra first, right? Always, always, always algebra first. So I've got -x squared and a -x squared is a -2x, but I've got 5 and 3 is going to give me 8 minus that 2x squared dx. And we could do this all day long, right? Easy integration. So that leaves me with 8x minus a 2/3 x cubed, and I'm taking that from a -2 to 2. Good. You should not have any extra steps in this problem. You're not breaking up this polynomial to look at this independently. These are the steps you need to have. You need to have this step up here just so I can see you know how to do the formula for the curves. Algebra this, put it together obviously, and then right here. Now I'm going to take the top minus the bottom. Fundamental theorem of calculus part 2, right? It's the one we use all the time. 8 minus 2 minus a 2/3 of 2 cubed minus 8 times -2 minus a 2/3 of -2 cubed. And then clean it up. What's 8 times 2? 16 minus a 16/3 minus a -16. And then that's a negative times a negative because this is cubed, right? So that'll be a positive 16/3. And then go ahead and distribute those signs so that we can see what's happening there. Okay, let's put all this together, and what do you get? We get 16 plus 16 is 32 minus a 32/3. If you get that common denominator here, it's over 3. What's 32 times 3? 96. Yeah, okay. So 96 minus 32 is 64/3. And that, ladies and gentlemen, is the area. All right? Not bad, right? Yeah, it's not bad at all. Okay, something else that I want to show you. So yes, I'm going to squeeze this back. Here, we did our graph, right? And we physically saw where these two intersected. When you're looking at these two graphs, you are going to have to graph, so you need to know how to graph. But you know this starts up here at 5 and it goes down because I've got that negative coefficient in front of a quadratic. We know about quadratics because you've had algebra as a prerequisite. But you know this is starting down here at -3 and it's positive, so it's a U going up. This one's going down, so that stands to reason. Something else you can do, if I'm looking at this, is I'm saying, where do these two functions intersect? And that also means, where are they equal? So just as a little side note here, because we've got this room, I'm going to put in here, go blue, to find the interval, you could also do this. 5 minus x squared is equal to x squared minus 3. Set those two functions equal. Where those two functions are equal, that means they intersect, right? So I am going to add this x squared because I want to keep my coefficient positive, and I'm going to subtract 5. So I now have, no, I'm not going to. I'm not going to subtract 5. I'm going to add 3 because I'm going to get those by themselves. I'm going to add 3. And now I have 8 is equal to a 2x squared, right? Because that subtracts off, that subtracts off. Divide both sides by 2. X squared is equal to 4. And then you can use the square root property. Remember, anytime you make the square root symbol, you have to write plus or minus. So these intersect at positive or negative 2, and those are the bounds. I know this is going from negative 2 to 2 because that's where my two functions intersect. Just another way, right? There's more than one way to find these bounds, so I just want to make sure that you know. Sometimes it's easier to set those equal and solve for the bounds algebraically versus drawing your graph. Sometimes the graph is easier, right? That's just kind of how that works. Okay, especially when you kind of have wonky-donkey graphs, sometimes it's easier just to set those equal. All right. Okay. Very good. Let's try some more here in just